In the next series of lectures, I'm going to discuss a different model or theory for covalent bonding, and it's Vesper theory. So this is going to build on Lewis bonding theory. As I said, we'll set a foundation and then we'll change it. And we'll keep adding to it to build a better picture of covalent bonding. This is that next layer to understanding how this works. So let's start with just defining what this is. Vesper, which is like weird, stands for valence, shell, electron, pair, repulsion theory. And it's a name I can never remember, but I can always remember Vesper. So Vesper theory states that Coulombic forces, so remember, Coulombic goes back to Coulomb's law, which means the repulsion of like charges and the attraction of opposite charges. So Coulombic forces create repulsion between electron groups in a molecule. So that's because our electron groups are both negative. Electron groups are lone pairs of electrons or single, double, triple bonds. So bonded atoms or lone pairs. And these groups are most stable when they're far apart from each other as possible while still being covalently bonded to some central atom. And that central atom piece is really key. So what we're looking at is we're looking at around this central atom, how do the atoms that are bonded or the lone pairs arrange themselves in space? And it turns out they're going to try to get away from far away from each other as possible, just to minimize the repulsions that occur between the the electrons, those negative charges that will repel one another. And so this phrase electron group is always a little confusing when you first learn about it, since we want to describe anything that is a ball of negative charge. Because anything that's a negative charge coming up to a negative charge will repel each other. So this is going to include for covalent bonds lone pairs or the atoms that are bonded to that central atom. So the bonding electrons. Okay. And so this is going to help us build a picture of how these molecules look in 3 dimensions. Our Lewis structures have been 2-dimensional and don't really reflect how this would look in space. But this will allow us to think about things in 3 dimensions. And again, this theory is very much a pattern that we have imposed based on our observations. So it's more of a bookkeeping method, a prediction tool, rather than a very clear picture of what is happening in the molecule. So keep that in mind. We still have a giant asterisk on everything we're doing, which says this is a great predictive tool, even if it isn't describing exactly what is happening in the molecule. So a little more detail on Vesper theory. So each lone pair of electrons will constitute one electron group on the central atom, and each bond will constitute one electron group to the central atom as well. It doesn't matter if it's single or double or triple. All that matters is the number of atoms that are connected around this central atom. So let's just take water as an example. So water has 4 electron groups. It has 2 lone pairs and 2 single bonds. And so we have our 2 lone pairs right here. Let's do it like this. And then we have our bonding electrons right here that go to the hydrogen atoms. And our Lewis dot structure might actually be a little bit easier to see. We've got this 1, 2, 3, 4 electron groups around that oxygen. And so they're going to arrange themselves to be as far apart as they could be in 3 dimensions. And so in 3 dimensions, the best you can do is arrange 4 things about 109 degrees apart from one another, 109.5. And in water, we see a bond angle of 104.5, which is really close. And that bond angle is just looking at the angle between the oxygen and the 2 hydrogens. And so what's happening is these lone pairs are taking up space. These bonded atoms are taking up space. And we'll see that these lone pairs actually take up a little bit more space, which I hope I talk about later, but in case I don't, it's when you have your oxygen bonded to your hydrogen, right? This lone pair of electrons, it's attracted to both the centers of the oxygen and the hydrogen. And so it actually makes kind of a smaller shape than the lone pair on the oxygen, which isn't actually bonded to anything else or attracted to anything else on the other side. So it kind of fans out more and takes up more space. And that kind of contracts that bond a little bit smaller than the 109. Anyway. So using Vesper theory, we can predict the basic molecular shapes that exist. And so these geometry names I'm going to talk about in bond angles, these are all around a central atom. And we'll first start by looking at super simple molecules with only one central atom. But most of chemistry isn't that simple. And so when we describe geometries, it's always in reference to the central atom. And in large molecules, you'll have multiple of these central atoms. And so you won't have just one name for a molecule's geometry. Rather, you will have many names for the geometries at any central atom. So that molecular shape is, I think, a misleading term. All right, so let's walk through these. Our simplest one we can do would have 2 electron groups. And it'll be 2 bonded atoms rather than any lone pairs. And what it would look like is a totally linear molecule. So here's one, a carbon bonded to 2 oxygens. And the furthest I can get them away from one another in space is 180 degrees. And so they'll go as far apart as they can get. And so we'll have a bond angle of 180 degrees, and we'll have a name for it that we call linear. So now the next thing we could do is have 3 electron groups. And this name will be trigonal planar, or some books say trigonal planar triangular, which is a little harder for me to say. So I always go with trigonal planar. There's 4 atoms involved in the picture, but there's 3 electron groups around that central atom. And in this case, it's 3 atoms bonded rather than lone pairs. And we're not going to worry about lone pairs at first. And so we would have something that looked like this. There we go. So I have 1, 2, 3 things spread apart as far as I can get them in 3-dimensional space, which is going to be 120 degrees apart from one another. And so we get this 120-degree bond angle between any 2, so any combination of 3 of the atoms in this. And that bond angle is the same no matter which kind of set of 3 atoms you look at. All right, next, well, let's look at 4 electron groups, all atoms still. We won't bring into account lone pairs yet. That's going to give us a shape that we call tetrahedral. Now, our carbon atom usually bonds to 4 things, right? So it forms a lot of tetrahedral compounds. Here it is. So this is a lot like the water example that we talked about previously. This looks like a jack if you've ever played jacks. And it has 4 things around it, but this time they're all atoms. And so that angle that's in between them all right here is 109.5. And since there's 4 things bonded to that central atom, it gets that name tetrahedral. And what it really looks like to me is like a triangle that's up a little bit with a top. So it looks like a 3-sided pyramid in a way. All right, next up, we have trigonal bipyramidal, which I haven't built, so I'm going to pause. So now when we have 5 electron groups, and we're just looking at everything being a bonded atom right now, we're going to have a geometry that we call trigonal bipyramidal. It's a big word, right? And here's what it looks like. So a trigonal bipyramidal structure is going to have 2 atoms kind of 180 degrees apart. And then if you look down the center, there's 3 atoms in what we're going to call the equatorial plane, but we won't worry about that for now, that are 120 degrees apart right here. And so the bond angles that we have are 90 degrees and 120 degrees. So we've got 2 different types. There's that 120 and there's that 90-degree bond angle. We won't worry about the bond angle here. It's 180 because there's a closer atom to describe it. And so that'll have a bigger impact on it because that's where we're actually having the repulsion take place between our electron groups. All right, now if we have 6 electron groups, Then we're going to get to what we call an octahedral structure. And so while the previous one, Trigonal Bipyramidal, was kind of like a three-sided pyramid diamond thing, this one's going to be a four-sided pyramid on the top and the bottom. So here's what it looks like. So in this case, we have 6 atoms around a central atom, right? Or 6 groups. So we have 4 that are all 90 degrees apart in one plane. And then you can look up and we have another 90-degree angle for the 2 that are on the top and on the bottom. And so looking at this, trying to find the best angles for you to see. This is our octahedral geometry. And all of my bond angles here are 90 degrees. And for some of us, visualizing these things in 3 dimensions comes easily. And for others, it does not. Our lab for this material will incorporate building things that you can hold in your hand and turn around and look at, as well as online simulations for that, to try to help you visualize these in your mind's eye.